The air conditioning system and its components. An automotive air conditioning system is a closed, pressurized system. It consists of a compressor, condenser, receiver, or dryer, or accumulator, expansion valve, orifice tube, and an evaporator. In a basic air conditioning system, the heat is absorbed and transferred in the following steps. Refrigerant leaves the compressor as a high-pressure, high-temperature vapor. By removing heat via the condenser, the vapor becomes a high-pressure, high-temperature liquid. Moisture and contaminants are removed by the receiver, or dryer, where the cleaned refrigerant is stored until it is needed. The expansion valve controls the flow of refrigerant into the evaporator. Heat is absorbed from the air inside the passenger compartment by the low-pressure, warm refrigerant, causing the liquid to vaporize and greatly decrease its temperature. The refrigerant returns to the compressor as a low-pressure, low-temperature vapor. To understand the operation of the 5 major components, remember that an air conditioning system is divided into 2 sides, the high side and the low side. High side refers to the side of the system that is under high pressure and high temperature. Low side refers to the low pressure, low temperature side of the system. The compressor. The compressor is the heart of the automotive air conditioning system. It separates the high pressure and low pressure sides of the system. The primary purpose of the unit is to draw the low pressure and low temperature vapor from the evaporator and compress this vapor into high temperature, high pressure vapor. This action results in the refrigerant having a higher temperature than surrounding air and enables the condenser to condense the vapor back to a liquid. The secondary purpose of the compressor is to circulating or pump the refrigerant through the air conditioning system under the different pressures required for proper operation. The compressor is located on the engine end, is driven by the engine's crankshaft via a drive belt. Although there are numerous types of compressors in use today, they are usually one of 3 types. Piston compressor. This type of compressor can have its piston arranged in an inline, axial, radial, or V design. It is designed to have an intake stroke and a compression stroke for each cylinder. On the intake stroke, the refrigerant from the low side of the system, or evaporator, is drawn into the compressor. The intake of refrigerant occurs through intake reed valves. These one-way valves control the flow of refrigerant vapors into the cylinder. During the compression stroke, the vaporous refrigerant is compressed. This increases both the pressure and the temperature of the heat-carrying refrigerant. The outlet, or discharge side reed carrying refrigerant. The outlet, or discharge side reed valves then open to allow the refrigerant to move to the condenser. The outlet reed valves are the beginning of the high side of the system. Reed valves are made of spring steel, which can be weakened or broken if improper charging procedures are used, such as liquid charging with the engine running. A common variation of a piston-type compressor is the variable displacement compressor. These compressors not only act as regular compressors, but they also control the amount of refrigerant that passes through the evaporator. The pistons are connected to a wobble plate. The angle of the wobble plate determines the stroke of the pistons, and is controlled by the difference in pressure between the outlet and inlet by the difference in pressure between the outlet and inlet of the compressor. When the stroke of the pistons is increased, more refrigerant is being pumped, and there is increased cooling. Rotary vane compressor. The rotary vane compressor does not have pistons. It consists of a rotor with several vanes, and a carefully shaped housing. As the compressor shaft rotates, the vane and housing form chambers. The refrigerant is drawn through the suction port into these chambers, which become smaller as the rotor turns. The discharge port is located at the point where the gas is completely compressed. No sealing rings are used in a vane compressor. The vanes are sealed against the housing by centrifugal force and lubricating oil. The oil sump is located on the discharge side, so the high pressure tends to force it around the vanes into the low pressure side. This action ensures continuous lubrication. Because this type of compressor depends on a good oil supply, it is subject to damage if the system charge is lost. A protection device is used to disengage the clutch if pressure drops too low. Scroll-type compressor. The scroll-type compressor has a movable scroll and a fixed or non-movable scroll that provide an eccentric-like motion. As the compressor's crankshaft rotates, the movable scroll forces the refrigerant against the fixed scroll and toward the center of the compressor. This motion pressurizes the refrigerant. The action of a scroll-type compressor can be compared to that of a tornado. The pressure of air moving in a circular pattern increases as it moves toward the center of the circle. A delivery port is positioned at the center of the compressor and allows the high-pressure refrigerant to flow into the air conditioning system. This type of compressor operates more smoothly than other designs. Refrigerant oils. Normally the only source of lubrication for a compressor is the oil mixed with the refrigerant. Because of the loads and speeds at which the compressor operates, proper lubrication is a must for long compressor life. The refrigerant oil required by the system depends on a number of things, but it is primarily dictated by the refrigerant use in the system. R12 systems use a mineral oil. Mineral oil mixes with R12 without breaking down. Mineral oil, however, cannot be used with R134A. R134A systems require that a synthetic oil, polyalkylene glycol, or PAG be used. There are a number of different blends of PAG oil. Always use the one recommended by the vehicle manufacturer or compressor. Failure to use the correct oil will damage to the compressor. Most often, when a system has been converted from R12 to R134A, ester oil will be recommended. Since there may be some mineral oil and R12 still in the system, it is important to use an oil that will mix well with the residue and not break down. Ester oil mixes well with mineral oil because it is hydrocarbon-based. Compressor clutches. Every compressor is equipped with an electromagnetic clutch as part of the compressor pulley assembly. It is designed to engage the pulley to the compressor shaft when the clutch coil is energized. The purpose of the clutch is to transmit power from the engine to the compressor and to provide a means of engaging and disengaging the refrigeration system from engine operation. The clutch is driven by power from the engine's crankshaft, which is transmitted through one or more belts to the pulley, which is in operation whenever the engine is running. When the clutch is engaged, power is transmitted from the pulley to the compressor shaft by the clutch drive plate. When the clutch is not engaged, the compressor shaft does not rotate, and the pulley freewheels. The clutch is engaged by a magnetic field and disengaged by springs when the magnetic field is broken. When the controls call for compressor operation, the electric circuit to the clutch is completed. The magnetic clutch is energized, and the clutch engages the compressor. When the electrical circuit is opened, the clutch disengages the compressor. Two types of electromagnetic clutches have been in use for many years. Early model air conditioning systems used a rotating coil clutch. The magnetic coil, which engages or disengages the compressor, is mounted within the pulley and rotates with it. Electrical connections for the clutch operation are made through a stationary brush assembly and rotating slip rings, which are part of the field coil assembly. This older rotating coil clutch, now is limited use, has been largely replaced by the stationary coil clutch. With the stationary coil, wear has been measurably reduced, efficiency increased, and serviceability made much easier. The clutch coil does not rotate. When the driver first energizes the air conditioning system from the passenger compartment dashboard, the pulley assembly is magnetized by the stationary coil on the compressor body, this engaging the clutch to the clutch hub that is attached to the compressor shaft. This activates the air conditioning system. Depending on the system, the magnetic clutch is usually pressure controlled to cycle the operation of the compressor, depending on system temperature or pressure. In some system designs, the clutch might operate continually when the system is turned on. With stationary coil design, service is not usually necessary, except for an occasional check on the electrical connections.